So we're going to study some interesting cases of finding limits. And let's begin by, first of all, recording some interesting properties of limits that have to do with operations between functions. So suppose that the limit as x tends to a of f of x is equal to L, and the limit as x tends to b of g of x is equal to m. Then the limit as x tends to a of f of x plus g of x is L plus m. The limit as x tends to a of f of x times g of x is L times m. And if x is different, if m is different from 0, then the limit as x tends to a of f of x over g of x is equal to L over m. Okay, so these are properties that we saw for the case of sequences, and they're true for functions. And we should also note a couple more things that are true here. So first of all, if you take the limit of the constant function, call it c, then that limit is simply going to be c. And if you take the limit of the identity function, then this is going to be simply a. And this is actually kind of funny because if you read it, you will see that it's really a tautology, meaning as x approaches a, x approaches a. That's exactly what we're saying here. So there's not even a reason to try to justify it. But what is important here is to understand that the limit as x tends to a of p of x for any polynomial function is equal to just p of a. So you want to find the limit for a polynomial function. All you need to do is just plug in. And why? Because a polynomial function is made up of the identity function by just multiplying it with itself. I mean, think about it. If somebody gives you the polynomial 3x cubed minus 2x plus 1, what is this really? It's 3 times x times x times x minus 2 times x plus 1. And so you have just multiplication and addition. And you have the constant function, or constant functions 3, negative 2, and 1, and the identity function x appearing. And for each of these functions, you simply plug in. So hence, for their combination, you also plug in order to compute limits. And if you have the quotient of two polynomials, then you're going to get p of a over q of a, assuming that q of a is different from 0, of course. This is in the case that p of x and q of x are polynomials. Now, it's interesting to see that one can prove more general properties. That is, there are more cases in which we can substitute. So, for example, if you have something like, and let's just throw this in, there are many more situations that one could describe. But if, let's say, you have the kth root of some polynomial, then you can simply plug in, and this will be kth root of p of a. So let's just notice this. It's fair to say here that in most cases, with most functions that we're going to encounter in this course, you can just plug in order to compute limits, even though structurally, from a formal point of view, we do not plug in when we wish to compute limits. We would like now to focus on some examples. So first of all, let's note that if somebody gives us a limit where plugging in is possible, then that's all that we will do. So let's say that we want to compute this limit. How are we going to compute this limit? Just plug in 1, and this will give you 2/3. Okay, exactly because finding the value of the function at this point is possible, that implies right away that this is indeed the correct limit. Okay, let's look at interesting cases now. So let's begin with the following example. What is the limit as x tends to -1 of x to the 5th plus 1 over x cubed plus 1? If you were to try to find this limit, then you would see that you would get 0/0. So this is not what you can do. If you have a 0/0 situation, what you do is you apply synthetic division to both the numerator and denominator and hope that upon doing a cancellation, you will not have a 0 situation on the denominator. So here, by applying synthetic division, we're going to show the synthetic division in a moment. We will get x plus 1 times x to the 4th minus x cubed plus x squared minus x plus 1 over x plus 1 times x squared minus x plus 1. We have this very agreeable cancellation, and we get the limit as x tends to -1 of x to the 4th minus x cubed plus x squared minus x plus 1 over x squared minus x plus 1. And now if we plug in, what are we going to get? You can get rid of the limit notation now because we're plugging in. So we're going to get -1 to the 4th minus -1 to the 3rd plus -1 squared minus -1 plus 1 over -1 squared minus -1 plus 1. And if we pay close attention here, we will realize that each of these things is actually 1. So this is 1. This is -1, but with the extra negative sign in front, that's 1. This is also 1. This again -1, but with the extra negative sign, it's 1, and this is 1. This is 1, this is 1, and that is 1. So finally, what do we find? We find 5/3. Okay, just to be on the complete side here, let's also show this synthetic division. So for the synthetic division on the top, we have 1, which is 5th degree, and then we need a 0 for the 4th degree, 0 for the 3rd degree, 0 for the 2nd degree, 0 for the 1st degree, and then we have 1. What are we dividing by? X plus 1, which means that the number is -1. So we bring down 1, and that gives us -1 times 1 is -1. So we write it here, we add it, then we multiply again -1 by -1, and we write what we find here, 1, and then we add it, and then we multiply -1 by 1, and we find -1, and then we add it, and then 1, 1, and finally -1, 0. So here are the numbers that we get. That justifies the synthetic division on the top. The synthetic division on the bottom is even simpler. We will have 1, 0 for 2nd degree, 0 for 1st degree, and then 1. We have the -1 here, bring down 1. -1 times 1 is equal to -1 that we write here. We add it. Then -1 times -1 is 1. we add it, and finally negative 1 times 1 is negative 1, which we added here, we get our 0, and here are the coefficients of the of what we find upon doing the synthetic division that justifies the denominator, and our example is complete. Okay, why don't we do a very similar example by just tweaking this a little? So let's find, for example, the limit as x tends to negative 2 of x cubed plus 8 over x to the 5th plus 32. As I told you, this is going to be pretty much the same example with a small tweak. So why don't you pause the video and try to do this example, and then check your work in what's going to follow right away, which is this. If we try to plug in, then we get 0 over 0, which means that we're going to try to perform our synthetic division. So this will be x plus 2. And interestingly enough, what we will find is x squared minus 2x plus 4. And at the bottom, we will get something much more interesting, x plus 2. And it will be x squared, x to the 4th minus 2x cubed plus 4x squared minus 8x plus 16. And now we have our cancellation. And this will be the limit as x tends to negative 2 of x squared minus 2x plus 4 over x to the 4th. We could have skipped this step and just go directly to plugging in, but let's write it once and see it. And now I can plug in, and hence I can skip the limit notation. So what do I get? I get minus 2 squared minus 2 times negative 2 plus 4 over minus 2 all raised to the 4th power minus 2 times negative 2 to the 3rd power plus 4 times negative 2 to the 2nd power minus 8 times negative 2 plus 16. It's kind of interesting. What you get on the numerator is pretty much the number 4 3 times. So you get 4 plus 4 plus 4, which is 12. What you get on the denominator is the number 16 5 times. How much is 16 times 5? That would be 80. And you can leave it like this, or you can do a simple cancellation with 4, and that will be 3 over 20, which is our final answer. Just again, to be on the complete side, let's do the synthetic divisions here. So we will have 1, 0, 0, and 8 for the top, and you have the number negative 2. So bring down 1. Negative 2 times 1 is negative 2. We add it. Negative 2 times negative 2 is 4. We add it. Negative 2 times 4 is negative 8. When we add it, we get our fail-safe 0. And here are the coefficients that justify what we got on the top. How about the bottom? For the bottom, we have 1, 0 for 4th degree, for 3rd degree, for 2nd degree, for 1st degree, and then we have 32. And here we have negative 2. So we bring down 1. We multiply by a negative 2 and we find negative 2. We add it, it's negative 2. Negative 2 times negative 2 is 4. We add it. Negative 2 times 4 is negative 8. We add it. Negative 2 times negative 8 is 16. We add it. Negative 2 times 16 is negative 32. Here's our fail-safe, and we get these numbers, which are exactly the numbers that we used on the top, on the bottom. Okay, so our example is complete. Let's do one more example of this type. Now that, so let's do the limit as x tends to 1 of x to the 4th plus 5x squared minus 6 divided by x cubed plus 4x minus 5. So something along these lines. Okay, please pause the video and try to figure out what this limit is. It is 0 over 0, but let's make sure that we can get it right. So in any case, let's perform our two synthetic divisions here. So we will have 1, 0, 5, 0, and -6. And we're dividing by x minus 1, which means we need to write the number 1. So this will be, again, before starting anything, we should have noted here that if we plug in 1, then we get 0 over 0. That's always the very first step. Okay, let's go back to our synthetic division. So we find 1, we write it here, we add it, and then again 1, that gives us 6, and then 6, we add it, that's 6, and then 6, that's 0. So here are the numbers. So this will give us the limit as x tends to 1 of x to the third. Oops, let's write first of all x minus 1 times x to the third plus x squared plus 6x plus 6 over. Now let's do this for the denominator. We will have what? 1, 0, 4, -5, and then we have the number 1 here. Bring down 1. 1 times 1 is 1. We write it here, we add it. Then we again multiply 1 by 1. We write it here and we add it. And here comes our failsafe that gives us 0 here. So what we get is x minus 1 times x squared plus x plus 5. So finally, we have a very agreeable cancellation. And this gives us the limit as x tends to 1 of x cubed plus x squared plus 6x plus 6 over x squared plus x plus 5. Now it's plugging time. We drop the limit notation, and that will give us, if you plug in, I think it's pretty straightforward to see that you get 14 on the top and you get 7 on the bottom, which gives you a very nice number 2 here. And that's it. Now, we would like to do apply one more kind of trick. And to show this trick, actually it's a very, very nice trick. Let's take a look at the following situation. So let's say that you have the limit as x tends to 1 of square root of x plus 3 minus 2 over x minus 1. Okay, so first of all, it's important to notice that synthetic division does not work here, simply because we don't have a polynomial on the top. But if we try to plug in, we will still get 0 over 0, which means that we might still desire to have some sort of cancellation. But how are we going to achieve this cancellation? And the answer here is kind of a little tricky. It would be really nice if instead of having square root of x plus 3 minus 2, we had the square root of x plus 3 minus the square root of 2, minus the square of 2, which would have been x plus 3 minus 4, which is exactly x minus 1. It would have been so nice, but we don't have it. We don't have it. So what do? We actually multiply by the so-called conjugate quantity, which is exactly the same thing with a plus instead of a minus. The reason behind this is if you have the difference of two things and you multiply by the sum of the two, of the same two things, then what you get is a squared minus b squared. This very, very nice identity is sometimes referred to as the difference of squares identity. And so what we need to do here in order to apply it is multiply by the conjugate quantity, which in this case is going to be square root of x plus 3 plus 2. But wait a moment. You can't just multiply out of the blue because you felt like multiplying. Okay, to balance the whole thing out, you need to also divide by it. Okay, so that's how you do it. So you think that you need that square root of x plus 3 plus 2 on the top. If you do so, fine, multiply by it, but then divide also by it so that everything can be balanced out. And of course, once this happens, then you will get the limit as x tends to 1 of square root of x plus 3 square minus 2 square over x minus 1 times square root of x plus 3 plus 2, which will give you the limit as x tends to 1 of x plus 3 minus 4 over x minus 1 times square root of x plus 3 plus 2, which is the same thing as the limit as x tends to 1 of x minus 1 on the top over x minus 1 times the square root of x plus 3 plus 2. So a little bit of interesting algebra here, but we finally reached the upshot of this whole process, because now we can cancel these two things. Be careful on the top. It seems that nothing is left, but what is left is the quantity 1. And on the bottom, we get square root of x plus 3 plus 2. Finally, we can plug in. And when we do plug in, we drop the limit notation. And we get square root of 4 plus 2. Square root of 4 is 2. So 1 plus 2, 1 over 2 plus 2, which is 1/4, which is our final answer. Okay, a very nice little example. Again, we call this the conjugate quantity trick. And let's do one more such example. So let's try to find the limit as x tends to 3 of square root of x plus 6 minus 3 over, let's say, x squared minus 9. Okay, let's consider this. So on the denominator, you will have to do a factorization, but on the top, you will need to use the conjugate quantity. So why don't you pause the video, try to solve this in the way that we solved it before, and then we'll see if you do it the right way. Okay, so let's see how it's done. So we will multiply and divide by the conjugate quantity, because the moment we try to plug in, we get 0 over 0. So we will have square root of x plus 6 minus 3 times square root of x plus 6 plus 3. Remember that you need to do this on the denominator, but on the denominator also factor out x minus 3, because that's what is responsible. So you can do a synthetic division. That's what's responsible for the 0 on the denominator. And then multiply by square root of x plus 6 plus 3. So you can see that the new thing that has been inserted appears both on the numerator and on the denominator. So it's really as if it's not there. It is there to make our life easier, but nothing has changed from the point of view of the balance of the inequality, of the quantity. So in any case, now the top can be rewritten as square root of x plus 6 square minus 3 square over x minus 3 times x plus 3 times square root of x plus 6 plus 3. So this is going to be the limit as x tends to 3 of x plus 6 minus 9 over x minus 3 times x plus 3 times square root of x plus 6 plus 3. And this will be equal to the limit as x tends to 3 of x minus 3 on the top over x minus 3 times x plus 3 times square root of x plus 6 plus 3. And how much is this? Now you have your cancellation finally that will rid you of the quantities that are 0. And we will have 1 over x plus 3 times square root of x plus 6 plus 3. Finally, we have something, we have a quantity where we can plug in. We drop the limit notation, and that will give us 3 plus 3. And then we will have square root of 9 plus 3. I think the whole thing is 1 over 6 times 6, which is 1 over 36, which is our final answer. Okay. I would like to finish with one more example where we will have now 2 conjugate quantities, one on the top, one on the bottom. So let's look at this example. The limit as x tends to 2 of square root of x plus 7 minus 3 divided by square root of x plus 2 minus 2. Okay, let's consider this. Again, if you plug in 2, you will get 3 minus 3 on the top, because square root of 9 is 3. And on the bottom, you will get square root of 4, which is 2. 2 minus 2, also 0. So 0 over 0. So what do we do here? We need to get rid of 2. We need to use 2 conjugate quantities, one for the top, one for the bottom. So on the top, what exactly do we need? We need the conjugate quantity of square root of x plus 7 minus 3, which is what? It's square root of x plus 7 plus 3. And on the bottom, we need the conjugate quantity of square root of x plus 2 minus 2, which is square root of x plus 2 plus 2. What is important here is that in order to balance the whole thing out, we need to multiply and divide by what we inserted on the top and the bottom respectively. So on the top, I'm going to put an extra square root of x plus 2 plus 2. So this balances out the denominator. And on the denominator, I'm going to put a square root of x plus 7 plus 3, which balances out what we had on the numerator. Now everything is perfect. And what we need to do is just multiply these 2 things together and these 2 things together. And let's see what will happen. So we will get the limit as x tends to 2 of square root of x plus 7 square minus 3 square times the square root of x plus 2 plus 2 divided by the square root of x plus 2 square minus 2 square times the square root of x plus 7 plus 3. And what is that? This is the same as the limit as x tends to 2 of x plus 7 minus 9 times square root of x plus 2 plus 2 over x plus 2 minus 4 times square root of x plus 7 plus 3, which, of course, is much simpler than it really looks. This is x minus 2 times square root of x plus 2 plus 2 over x minus 2 times square root of x plus 7 plus 3. Finally, cancellation time. So this cancels with that, and now everything is really good, because everything you can see here is a plus. There will be no more zeros when you plug in. In fact, you can plug in right away. This will give you square root of 4 plus 2, and this will give you square root of 9 plus 3. This is the same thing as 2 plus 2, also known as 4, 3 plus 3, also known as 6, and you can even simplify it as 2/3 if you like. Okay, and that's the whole process. With this example, we complete the examples with the conjugate quantity trick. And thank you so much for watching.